As mentioned several times, even a point particle moving along a straight line has angular momentum about any axis you choose, although the value could be 0, of course. This can be seen in dramatic fashion, or dramatic-ish fashion, by watching two hover pucks collide. What we see is the two of them moving linearly, and when they collide, they start spinning around their common center, but they no longer move their center of mass because their linear momenta were opposed. It looks something like this. Right, we have one of them heading this way with linear momentum and the other heading that way with linear momentum. Their center of mass would be halfway between them. When they join, their total momentum is 0, so the center of mass doesn't move any further. But their angular momentum is not, because both of them, that's tending to spin around that direction, and this is tending to spin around the same clockwise direction. So they had some initial angular momentum since there were no external torques, and they are currently spinning at the end around a common center. Then they must have had angular momentum around that center before they collided. So there must be angular momentum locked up in along with that linear momentum. Remember that angular momentum will be the perpendicular moment arm times the linear momentum. So a bullet of mass m is shot at a hinged rod near the end of the rod. The rod was initially at rest and has a moment of inertia of I about an axis through the hinge. The bullet is fired at various angles theta to the rod, as shown in the top views given below, with initial velocity of v at a distance d from the hinge. Draw a blue circle around cases where the bullet has the greatest angular momentum, and a red circle around the cases where it has the least. Once again, we're going to draw the line of action for the linear momentum. For instance, in case A, it's this, so that we can find the moment arm, the shortest distance to that line of action, and then say that L is R perpendicular times P, but P is the same because M and V are the same. So it's just really R perpendicular that determines everything. Whoever has the greatest moment arm will have the largest moment of inertia, a large angular momentum. And so we just go through here and we say they're really just going to be d times sine of the angle, the way that the geometry's been worked out. And so we get the most when it is at right angles, and we get the least when it's the shallowest, which kind of makes sense, because if it had been 0 degrees and hit right along the rod, there'd be no angular momentum. All right, same setup. Not going to read it again. The angular speed with the bullet embedded after the collision is omega, and several students discuss the situation after it hits. Anne says the angular momentum of the rod plus bullet about the hinge after the bullet is embedded is the same as the initial angular momentum of the bullet about the hinge. Bella says the kinetic energy of the bullet before collision with the rod is equal to the rotational kinetic energy of the rod and bullet after. And Carla says the bullet going straight, so it does not have an angular momentum about the rod hinge, so we do not use conservation energy. But we can't really use conservation energy because we don't know how much energy is lost in heat, deformation of the bullet of the rod, and so on. Anne is actually correct. During the impact, there are no external torques, so the angular momentum must be conserved. The bullet is moving obliquely to the pivot, so it has some angular momentum, even though it's traveling in a line. BLA is incorrect because there's no reason to believe the forces acting are conservative. In fact, since the things stick together, we know the collision is not completely elastic, and some energy is lost to deformation, if nothing else. Carlos gets that right. He knows that energy conservation is not correct, but then is incorrect in asserting the bullet has angular momentum. This pretty much wraps up the toolkit for classical mechanics, and we sort of have a hierarchy that's worth looking at least a little bit. The most powerful tool we have is conservation angular momentum, followed by conservation linear momentum, followed by conservation energy, followed by rotational dynamics such as torques, followed by linear dynamics such as forces, and the least powerful technique is kinematics. It's a little funny that we sort of study it in the other order, but that's because it takes more abstraction to build why the more powerful tools are more powerful. Why is conservation angular momentum the most powerful? One, it's very often applicable. There are a lot of cases where there are external forces, but they're central, so you can still do angular momentum conservation. Two, when it fails pretty spectacularly, pretty quickly. In other words, you'll know right away whether it's the right approach or not, so you might as well check it. Likewise, linear momentum, which will fail relatively gracefully because it's 3 equations at once, and even if one direction ends up having momentum not conserved, the other directions probably still will. So again, it fails, and it fails gracefully. Conservation of energy is not as powerful because there are many forces that are dissipative or add energy to systems, and they might even be internal. So that it's very hard to keep track of what's going on, what goes on with these things. And then dynamics is I list as probably among the least powerful because it's so complicated. You have to keep track of directions, you have to keep track of vector additions, and so while it's relatively straightforward to state, it ends up being usually computationally difficult to use. Kinematics is powerful in that often you can recognize a kinematics problem right away, and then when you can, it's very easy to solve. But sadly, because of the restriction of constant acceleration, it's just not very common for interesting problems. It's sort of an ancillary rather than a central thing.